Ideally, like Wednesday or Friday, kind of play that by ear. Next class, so Monday, you guys are going to have a short memorization quiz on your integration formulas. So if you look at the 5-4 notes, these integration formulas. So I'll just supply you with like the integral side, and you have to give me the other half. So just memorization, I don't know, 10, 15 questions, something like that would be like 5 minutes, either you know it or you don't.
And only integrals?
Only integrals.
So you would just give us the first?
Just give you the one side and you supply the other. Yep. Okay. This is me trying to do you a solid to make sure that you have these things memorized, because like they ain't going away. The sooner you got them, the better off you'll be. But it'll just be a little 10-pointer or whatever, be test points. So you want to do well on it, but it's just like a little test pointer. This is the only table you need, is this guy right here. All your integral formulas are right there. Okie doke. Let's get after 5-5 then, and depending on what time is left, maybe we'll talk about test 5 format and take some questions from whatever we got. Okay? Sound good? Great. So, the fundamental theorem of calculus tells us to do an integral. Basically, all we're doing is an antiderivative, right? Which is great if there's an antiderivative formula that's directly applicable to what we're integrating. But if we have something like 2x times the square root of 1 plus x squared, right? Like, that's not any of those antiderivative formulas, right? But if I look at it and I kind of squint at it, this kind of looks like the 2x times square root of 1 plus x squared kind of looks like the result of a chain rule derivative, right? Where I have a composition of two functions times another function. So what we're going to do today is we're going to develop an integration technique that allows us to kind of anti-differentiate some of these chain rule derivatives. Okay with the plan? Okay. So we'll get back to this. So if we have some like chain rule derivative, and I want to find its antiderivative, what I'm going to do is I'm going to identify that inside function, and I'm going to set that equal to u. I'm going to make a substitution here. I'm then going to compute the derivative of u and make a second substitution for g prime of x times dx to be my dq, which basically is going to give me something that looks like this now to integrate. And the hope is that that function will be something I can use one of my anti-differentiation formulas on. Okay? So let's do some practice. I have a whole bunch of integrals here lined up that we're just going to kind of practice this technique on. Everybody's okay? We'll walk through the technique again. And this is the lesson. It's just getting used to this technique. just as an FYI, basically from this day forward, every integration that you're going to be, every section that involves integration will involve u substitution. It's going to happen all the time. You want to get super good at it as quick as you can, because it's going to be all over the place here for the rest of the semester. Okay. So I have the integral of x cubed cosine of x to the fourth plus 2 dx. What I want to do is I want to start by selecting my u. Typically, you want to pick the inner function. In this case, u should be x to the fourth plus 2. Everybody okay with that? The next thing I need to do then is to take the derivative of u with respect to x. The derivative of u with respect to x is du dx. The derivative of x to the fourth is 4x cubed. The derivative of 2 is 0. Okay? I'm going to multiply both sides by dx. Everybody's okay there? And now I'm going to look at what I have here. So I can replace the x to the fourth plus 2 with a u. I have an x cubed and a dx, but I don't have this 4 up here to make my substitution. Everybody okay? You see this? Small problem, right? What am I going to do? I'm just going to divide both sides of this equation by 4. Everybody's all right? And now, my x cubed and dx I can replace with du over 4. So let's go ahead and make our substitution. Is everybody okay with what I did? You see the substitution that took place? What do we notice about the integral that we have now? It's all in terms of the variable u. No more x's. Everybody all good? Yes, Ava.
Oh, how is it? Oh wait, that's a u, not a 4. Never mind. In the parentheses.
Yes, that's it. That's my bad habit. Okay. So this over 4, because it's a constant, I can just bring to the front. Everybody good there? That's one of my rules for integrals. Right? I can just pull those constants out front. And now what I want is the antiderivative of cosine u. So what is the antiderivative of cosine? That's the derivative of cosine is negative sine. The antiderivative of cosine is just sine. So we have 1/4 sine u, and then we have plus, because it's an indefinite, or indefinite integral. Everybody so far so good? Now the anti-differentiation is done, but we're not. Because the integral we're doing is in terms of what variable? X. My antiderivative I've written is in terms of what variable? U. So I have to fix that. All I need to do as my final step is to plug back in x to the fourth plus 2 for my u. And we're done. Okay. Let's do the next one. We'll hold your hand through one more, and then we'll take the training wheels off a little bit and let you guys try one. Is everybody okay? What should we pick for our u? 2x plus 1, right? Again, typically what I'm looking for when I'm choosing my u is I want the inner function of the composition. Typically. There might be some instances where you don't. We'll look at maybe an example of that later on. Okay. After I've picked my expression for u, I take the derivative of it. The derivative of u is du dx. And the derivative of 2x plus 1 is 2. Now, if I look at what I got, this is my u. We don't have any 2 floating around in here anywhere, right? So I'm going to divide that over when I multiply over the dx. I'll just kind of write that. Is everybody okay? Now I'm going to write my substitution. So I have square root u times du over 2. Everybody good with the substitution that was made? You see where everything went? I can pull the 1/2 out front, and I'll rewrite square root u as u to the 1/2. What's the antiderivative of u to the 1/2? Two-thirds u to the 3/2. Can you see it? Or do I need to slow down on the antiderivative there? Okay. U to the 1 plus 1/2 over 1 plus 1/2. And then I simplified. I did it in my head. Hopefully that's okay. So far so good? I simplify a little bit. Bing, bing. And then what else do I need to do? Get rid of the u. And I'm done.
Where does the du go after the second step in substitution? Like, why does it go there?
So you're talking about right here.
Yeah.
So remember, that du is just part of the integral symbol that's telling you the variable that you're integrating with respect to.
Okay.
Just like when we do like dx, when we take the derivative, that's telling us to differentiate with respect to x. The du at the end is telling us to integrate with respect to u. So it's just kind of part of the integral symbol. So when we do the antiderivative to the function, the integral symbol and the du just drop off.
Okay.
Is that
Yeah, that's perfect.
excellent? Okay, everybody's okay? Try the next one here on your own. I'll wait a couple of minutes, give you guys a little bit of a head start, then I'll start filling in behind you guys. But take a minute and try to work through this one on your own. And if you finish that one before I start writing, you can go ahead and start the one after that again on your own. But these two, I think, are pretty fairly easy, you know, U substitution integrals. Oh. Guys, I'm sleepy. You know? I think it's been the weather. You know, it's like that no sun winter phase here. I won't see the sun until March or something. Ugh. Michigan. So I'm just going to kind of periodically come in and write some steps in, so that as you're going, you have some checking that can happen. Sam?
What if we accidentally,
Yeah. So this fraction in the beginning, I could think of like that, right? It means the same thing. Now do you see why it's one?
oh,
So that's real common when you have a fraction. You want to probably think about like 1 over denominator times numerator. Often is a good way of kind of seeing it, especially when you're doing a U substitution here. Oh yeah. Guys feel okay?
the 1/4 calc multiplying that
To go negative 1/8,
and
yes.
you can just move the power to the half outside of the parentheses.
Well, it's because the 1/2 power is just attached to u, right?
Yeah.
And the u is this stuff. Is that, you see it? Again, it's one of those things like, once you look at it, it's like, oh, yep, okay, I see what happened. But again, if you're not sure, you should ask, no problems. I don't mind filling in some blanks. I sometimes leave some blanks in there intentionally to make you think about it, make sure that you got it. It's okay to ask if you're like, I don't see it. Go ahead and start on the next one. This one's probably easier. My 2 cents. I think this is the easiest one of the lot. Oh, excuse me. Thank you. It was balmy this morning, though. Like, I think it was 10 degrees when I went outside. That's like the warmest morning we've had in a little while. So, been a rough winter, guys. We were talking, I think it was back in like 18, where we had like the snowmageddon and then like the polar vortex behind it. It just was a mess. It's like we lost like a week of school. Do you guys vaguely remember that? You've been pretty young. Like 18, like in 18, where we had like a huge snowstorm and then the polar vortex right in behind it. So like it froze up all the snow if you couldn't get it off. It was a mess. That was the worst winter I could remember since this one. Hopefully you would pick u to be 5x. Oops. So it'd have dx is equal to du over 5. Antiderivative of e to the u is just e to the u. And then plug our u back in. I think that was the easiest one. Just as a expectation clarification, on any test or whatever, I do expect to see you labeling what your, like what your substitutions are before you make your substitution. That should be written down on your paper. Okay? In the past, I've had to fight with students about making sure they're doing this. Yeah, Sarah.
Is there like ever a situation where there's like multiple different answers for a substitution? Like I know not in these problems, but
Where you could, multiple different things you could choose as your u?
yeah,
Yes, but they'd all simplify down to the same thing in the end.
okay.
So that is possible, but it's also possible where like you pick the wrong thing to substitute and you're left with something that doesn't work either. So there's a little bit of freedom to that. All right. This next example you should make note of. There's a trick that we have to employ to do this problem. I will guarantee you that I will use the same trick on your test 5. So the same trick I use in this example will occur in test 5 somewhere in it. So if you're making notes, I would make note of that on this one. What are we going to pick as our u? Yeah, 1 plus x squared is the correct choice and the obvious choice, I think. So du dx then is going to be 2x. Notice there's no 2 up here. So what am I going to have to do? Yeah, divide the 2 over when I multiply over the dx. Does anybody see the issue? Yeah, sure. So Anthony says x to the 5th I can think of as like x times x to the 4th. So we have that. And this guy does that. They still have x's floating around, right? Does anybody see the trick? If I take this equation and I subtract 1 from both sides, u minus 1 is equal to x squared. X to the 4th is x squared squared. So I can make another substitution and do that. So if we piece this all together, that's my integral. Does everybody see the substitutions that I made there? This is the trick where you have to do a second substitution using rearrange your equation for u to make a second substitution. I should guess a third substitution. That's the trick that I promise I'm going to recycle on your test 5. There will be an integration problem where you have to employ that same trick. Oh no! It'll be okay. You guys can handle it. The way this is currently written, am I ready to anti-differentiate this? No. What am I going to need to do? Okay, I can pull the 1/2 out front, sure. But it's still not something I can anti-differentiate from there. What am I going to need? I'm going to need to do some algebra to, what's that? Yeah, so I should expand the u minus 1 squared, so FOIL that out. Everybody okay with what I did there? Still not ready to anti-differentiate that. Why not? Yeah, because the multiplication going on between the two functions. But Anthony says, what if I just distribute that through? Okay with the algebra I did there. Maybe I can put that up higher if you're probably ducking and peeking around the corner trying to see it.
What?
Your head's too big. Is everybody good to hear? Now I'm ready to anti-differentiate, because now I can take these one at a time to anti-differentiate. Is everybody okay? You see the fractions where they came from? Okay. What's the antiderivative of u to the 5/2? Good. 2/7, u to the 7/2. Okay. So the trick how Anthony's doing this so quickly, 5/2 plus 1 is 7/2, and the coefficient will be just the reciprocal of that. So that's how he's doing it so quickly. So he's doing the exponent first, and then the reciprocal is the coefficient in front. Okay. Now I'm going to distribute the 1/2 through and put the x's back in. And we're done. And that mess is my final answer. I distributed the 1/2 through, right, to simplify some of those coefficients. What do you guys think? Do you see it on what I did? Yes, Eva.
Will we have to simplify it on the test, or could we, like, even though it'd be more messy, just substitute preview?
So, yeah, that's a good question. The simplifying, no, you would not have to do on the test. Once the calculus is done, you can be done. But if you don't put the x back in, the problem is not completed. You would not receive full credit if the x's are not substituted back in. So whether you do all the cleanup at the end, that's neither here nor there, but the x's have to get substituted back in at the end. How are we feeling so far? Is this going okay? Going slow enough? Trying to be very careful here. Again, this is a skill that you're going to use basically every day from here on out. So I want to make sure that you get good at this. Matthew.
Sorry.
That's okay.
Back over getting u minus 1.
Yes. So we have this equation,
Yeah.
right? What I did is I had some extra x's that I had to substitute a u in for. This is my ticket. I just subtracted 1 from both sides. And that gives me another expression for x in terms of just u's that I can then substitute in for those x's that didn't have a home. You see it? Integral of tan x dx. Oh, well, what's the antiderivative of tangent? You have all those antiderivative rules, right? What's the antiderivative rule for tangent? So the derivative of tangent is secant squared. So the antiderivative of secant squared would be tangent, but that's not, right? Not what we're looking for here. Is there one? No. Okay. All right, well then, this is in the u subsection. Probably I should be doing some kind of u substitution here, but there's only one function, just tan x. I like that idea better. Why don't we do switch it? Sine over cosine, though, is probably the one we want to use because that has two functions in it. 1 over cotangent, still just one function. Okay. Which I pick as my u? Sine or cosine? Does matter. Nope. Cosine. Why cosine? So you'd want to think about it this way. Which one of those sine or cosine is in the composition? Cosine is the one that's in the composition, right? It's composed with 1 over x. Why cosine? Sine is not a part of a composition. Does that make sense? Okay. Again, if you tried picking sine, you're going to get yourself into a little bit of trouble because you're going to end up having to, like, you would get dx times cosine, but this is like dx over cosine, and just like it wouldn't work for you. If you want, we can try using sine and you can see what I'm saying. So again, u is going to be cosine. The derivative of cosine is negative sine. So negative du is equal to sine dx. So make my substitution. Somebody feel good so far? What's the antiderivative of 1 over u? There's a memorization quiz on this stuff coming soon. What? The natural log of absolute value, u. And I'm going to take that negative sign out front. Everybody okay there? And then I just plug my u back in. So again, in many situations, the absolute value might not matter. Here it should be there, since cosine could be negative or positive. You guys feel okay? Just as an aside here, if we had picked sine, we get this, right? The problem is that our integral is sine x times 1 over cosine times dx. And I don't have a cosine x times dx. I have a 1 over cosine x times dx. So the substitution won't work. Right? You see the issue? it looks like it's not working, you probably picked the wrong u. Feel good? You see why the sign wasn't going to work? Looks like it's going to. Looks like, oh, it shouldn't matter, right? Kind of did. All right. Let's look at some examples using doing a definite integral this time. What's the difference between an indefinite integral and a definite integral? The indefinite doesn't have bounds, so our answer is going to be a function. The definite integral has bounds, and our answer is a number. Okay? I'm going to show you two different ways to handle these definite integrals where there's a u substitution. Both ways are valid. It doesn't matter to me which way you use. I'll tell you my opinion as to which one I think is the better one. But they're both fine. It doesn't matter. And depending on the context, I might choose one over the other. But generally, I prefer one. So let's look at this guy. Start off as usual. There's my u and there's my dx. I'm going to skip some steps here and just kind of piece some stuff together. Is that okay with everybody? Where I pulled the coefficient out front and rewrote the square root as a 1/2 power. So I do my antiderivative. Everybody's okay? Why is there a plus c? Because it's a definite integral, right? No plus c's if the answer is a number. Plug my plug my value for x back in. I'll do this. Two times 4 plus 1 is 9. The square root of 9 is 3. 3 to the third is 27 times 1/3 is 9. 2 times 0 is 0. Plus 1 is 1. 1 to the 3/2 is 1. 1/3 times 1 is 1/3. 27 over 3 minus 1 over 3 is 26 over 3. Everybody okay with what I did there? That's kind of the naive method. That's kind of how you'd expect it to go. Is everybody okay with what I did? The method I prefer, particularly if I'm having to do something by hand, if it's a no calculator, I think this method makes everything a little cleaner from a computational standpoint, is I'm going to adjust my bounds of integration. So that I don't have to plug the x back in and make my function more complicated to deal with. So what I'm going to do is I'm going to take u of 0. So 2 times 0 plus 1, that's 1. I'm going to take the other bound, which is 4, and do u of 4. That's 2 times 4 plus 1. That's 9. And now what I'll do is I'm going to integrate from 1 to 9 that same u to the 1/2 du. These guys still simplify the same way. But now, because I've adjusted my bounds, I can plug those in directly. I don't have to plug the x's back in. So that's the advantage, particularly if you're doing this by hand. This computation is a lot easier, or less cumbersome anyways, than that computation. The more complicated your u is, the more benefit this has. Again, square root of 9 is 3, 3 to the third is 27, divided by 3 is 9. 1 to whatever power is 1, times a third is a third, and we end up with that same 26 over 30. I usually prefer to do things this way. This is, to me, a little cleaner computationally, especially if I had to do it by hand, like if it's a no calculator section. I think that makes things a little bit nicer because it shortens the computation for me. There's a little less substitution to do and like one last place to muck up having to simplify something. But it's, you have to remember to do it, right? You have to remember to adjust those bounds in the beginning. But it's easy to do that. All you're doing is plugging the bounds in to your equation for you. Easy to do that. That's usually a pretty simple calculation. I'm going to skip that next example and go to this one. So this is the integral from 1 to e, natural log x over x dx. What should I choose for my u? I want actually natural log. Why don't I want to pick 1 over x? Mr. Kulik, you said usually I want to pick the denominator. If I think about it, that's really what this thing is saying, right? What's the derivative of the natural log? 1 over x. Oh! Yes! That's wonderful. The derivative of x is 1. There's not a good way to get the natural, I can get the natural log back, or natural log x in there from that, but it's like a crummy substitution pattern. This is way cleaner. If I pick u to be the natural log of x. Then everything just like substitutes itself. I'm going to do the same bounds readjustment. So u of 1 is the natural log of 1, which is 0. The log of any log of 1 is 0. And then u of e is the natural log of e, which is 1. Oh, I like that. So this turns into the integral from 0 to 1 of u du, which is about the easiest stinking integral you'll ever see. Antiderivative of u is u over 2. Done. Is that okay? Again, you could do that without adjusting the bounds, that's okay to do that, to get the same answer. It's not too much different than this. I just find it a little cleaner to do it this way. You know what I mean by cleaner, right? Like things don't get as big. We have two special case formulas that can simplify our definite integral computation. So if you have an integral over, yes?
On the 2.5, is it using 6?
Yeah, so if I looked at example, no, I know.
What does that mean?
So it's because we did, that problem already. So just saying use your antiderivative you already computed. That's what it was getting at there. Does that feel okay? I was trying to save you time. So if I'm taking an integral over negative a to a, that's my cue. And as soon as I see like the integral from negative 1 to 1, or from negative 2 to 2, or from negative pi to pi, that gets my attention. Because it could be an instantaneous finish problem where I don't have to do any computation at all. Or it could be, well, I can make my life a little bit simpler problem, or maybe there's no help. Just depends on what that function is that I'm integrating from negative a to a. So the good one, the best case is if that function is odd, the integral is just 0. Doesn't matter what the function is, if it's an odd function. Doesn't matter what a is, as long as you're going from negative a to positive a, the integral is 0. So if you think about why this would be true, if I look at the graph of x cubed, the area below the x-axis and the area above the x-axis is equal, so they should cancel out and give you 0. Right? As long as I have an odd function. Less awesome, if I have an even function, I can just do that as 2 times the integral from 0 to a. Now that's a little bit of a help because computationally it doesn't get a lot easier number to plug in than 0, especially if I have to do it by hand, like plugging zeros in, pretty nice. And again, the reason why this would work, let's say you have y equals x squared. That area there should be the same as that area there. So it'd be the same thing as just taking that guy twice, right? Is everybody okay? Just to rehash some common odd functions. X cubed, right? What else? What? Tangent's odd, very good, yes. X to any odd power, right? Any odd root of x, like cube root, fifth root, etc., those are odd functions. Sine, also odd. The reciprocals of sine and tangent, also odd. Sine inverse, tan inverse, also odd. Those are probably the most common ones that we run into. Odd function plus odd function is another odd function. Okay. Odd function divided by odd function. Even or nothing. Yeah, it should be even. odd function plus even function, nothing. Can't say anything about that. I don't know, what else is there? Same rules for evens, right? Okay. If I look at this, x to the 6th, even. Well, I guess first I notice I'm going from negative a to a, right? X to the 6th, even, constant function, even, right? Because remember, this is like x to the 0, so it has an even exponent. Is okay? Even plus even is even. So that allows me to rewrite it as 2 times the integral from 0 to 2. Okay, well, do my antiderivative. And then I guess like, let's put it in. Uh, 256 over 7 plus 14 over 7, 270 over 7, I think. Yeah, mental math. So again, not much of a time saver, just this guy becomes 0. That's nice, right? It makes the arithmetic a little bit easier. I don't have to muck around with like adding or subtracting fractions, which cool. I love that, but not a tremendous time saver. Let's look at this guy. Again, I notice I'm going from negative 1 to 1. Ooh, maybe I got a time saver here. Let's look. Tangent is odd. 1 is even. X squared is even. X to the 4th is even. This whole denominator then is even. Odd divided by even is odd. So it's 0. Only when I go from like, negative a to a can I look for that shortcut. Okay? Only in that situation can I look for that shortcut. But it's a good one. If you catch it, woo-wee, that's a time saver. Right? If I looked at that, do I even have a way to compute that integral? Otherwise, if I tried to do that directly, Mr. Kulik, who's got a PhD in mathematics, I don't know that I have a good way. I don't know that that's one that you're even going to be able to do by hand. Maybe, but it'd be terrible. You'd have to find like a tan inverse in there somewhere. Or like 1 over 1 plus x squared. You have to do like a completing the square in the bottom, hoping to get to a tan inverse substitution, and then like you have to do like some inverse with the u. It would get messy real quick. It would be rough. Beyond the scope of what anybody would expect you guys to be able to do on an 18th. That's it for 5-5. Reminder, next time we have memorization quiz. We'll also do the 5-5 quiz on the MyAP. Okay. Talk a bit about the 15 minutes or something, right? Let's run through the test 5 format. If that's happening next week, probably some of us are going to want to start at least thinking about getting ready for that kind of thing over maybe if the weekend, or we catch a long weekend, because I think the left school tomorrow, but like, who knows? They don't ask me about it. Because I vote no, but nobody else. I think we're gonna go. So the two parts, you have 7 multiple choice questions in part 1, and a free response similar to those free response questions that was in the 5-3 homework quiz, which, by the way, most of you still haven't submitted. So you might have started it, but if you didn't hit submit at the end, I can't look at it to check them. I did want you to do those free response questions. Their reasoning being that, like, you're going to see something real similar to that on your test 5. Per Ava's request, in addition, on my Notre Dame in the announcements down at the very bottom, I let you guys know that I made a Delta Math assignment involving, like, these same kind of 5-3 problems. We're asking you to, like, do the integral of a graph that are very similar in style to these same FRQs, but they have a little bit more instantaneous response, and I'll walk through the answers for you. Don't feel like you need to do it. It is not required. It is optional. You can do parts as much as you want. I think the Delta Math estimated is like 2 hours worth of math problems on there. Do not feel like you need to do the whole thing unless you're like, yo, I need to get better at this because I know I don't know how to do it. And then it's like, well, maybe you do want to spend 2 hours doing this, and that's good time well spent because you get a lot of feedback instantaneously from it. And then in part 2, 3 multiple choices, 7 integrals. The integrals will be indefinite or definite, U sub, not U sub, all mixed together. You don't know what you're going to get until, you know, like you look at it and you have to decide what to do. And that's half the battle, right? Knowing what to do. And then I have 1 like Riemann sum calculation problem. I'll give you like a table of values and ask you to calculate the Riemann sum a couple of different ways. You know, whether it's left endpoints or right endpoints or midpoints or whatever. What do you guys think? That's the test format. So again, on the OneNote, I have a whole mess of practice multiple choice questions. In fact, I have 2 versions of the same stuff. I have some more FRQ practice questions. Some of these might be repeats of that other set that I gave you above, but again, more of this stuff. If you want practice, there's practice ones and keys attached to them all. Does everybody feel okay on that description for the test, what you really need to look over? Make sure you practice some of these multiple choice and the FRQs, as that's going to be the basis. And then you have to be able to do integrals by hand. Here's a function, you know, like integral of x squared or whatever. Like, you got to be able to do that kind of stuff, or the stuff we just did. Okay? Sound good? You guys have questions on stuff. We've got, I don't know, 10, 15 minutes. Questions on content, homeworks, homework quiz stuff, FRQ stuff. Ava.
The Delta Math, I just like signed up for the 3rd hour, but it's not showing up.
If you look at the past two, what is in there? Let's look real quick. That's embarrassing. I thought I did that. Maybe I assigned it to the wrong class. 5-3 practice. Oh, I see. It just hasn't posted yet. What do I need to do with that then? Edit. Oh, I see. We'll go back. That would be why. Oh my God, I picked one. I don't know, the 28th or something, whatever. Okay. Refresh and see if that pops for you. I'm glad you mentioned this.
Yeah,
Wonderful. Yes! Not a calculus question. Unless we want to talk about flow rates or something, but that's getting kind of gross now. Spherical shaped toilet. P is being added at this rate, while water is draining from the bottom at this rate. At what rate is the height of the water in the toilet changing? Gross. Grossest related rate problem you could come up with. Thanks, Mr. Boulay.
Why is it
So nothing, you guys feel okay? All right, dudes.